talk will be on cost semantics and static resource analysis for CUDA by Stefan Muller.
I got it.
Yeah. I'll let you know when you're close to it.
All right, so this morning, it's a little small, but we heard from Sade that maximizing parallel performance is minimizing data movement overheads. And I'm not going to argue with that, but I am going to add a caveat, which is that this is true if you're starting with a well-written kernel. So let's instead assume that you are a novice CUDA programmer, like myself, and you're not well-versed in all of the performance properties of CUDA, and in particular, there are a lot of kind of performance pitfalls that you can run into if you're not really aware of all of the ins and outs of the execution model and the memory model and all of that. And then you might end up with not a well-performing kernel where the bottleneck is actually your kernel code and not the data movement. So to get into what I'm going to talk about, I do need to give a bit of an overview of the execution model and the performance model of CUDA, since I would imagine not everybody is intimately familiar with it. So CUDA has a hierarchical model for threads and memory. So we have many, many threads. We group them into groups called blocks, and then many blocks form a grid. And similarly, the memory of CUDA also forms a hierarchy. So every thread has its own copy of local variables. Then threads within a block share access to a larger and slower shared memory. And then all of the blocks share access to an even larger, even slower global memory. There's a smaller grain grouping of threads called a warp. So generally, a warp will be a subset of a block. And a warp is fixed by the hardware to be a group of 32 threads. These groups of 32 threads, these warps, execute the same instruction in lockstep, so in a single instruction, multiple thread model. So they execute one instruction, but again, on different copies of local variables. So you could have the instruction increment x, your local variable, by your thread ID. So we have all the threads in the warp. They each have, obviously, a different thread ID. They each have, in principle, a different copy of x, but let's say that they all start off initialized to 0. They all execute the same instruction at the same time and end up with different values for x. So this leads to a lot of parallelism. It also can lead to a lot of unexpected behavior. So for example, let's say you write your kernel. CUDA looks just like C or C++. Let's say you say, OK, I know C, C++. I'll write my C, C++ code. It'll immediately go thousands of times as fast. Great. OK, that's unfortunately not the case. So let's say you write some code that looks like this, perfectly good-looking C code. But we now condition on whether the thread ID is even or odd. Now, the different threads within a warp are going to take different branches. So we have half the threads in the warp for which this condition is true and half for which is false. So in order to evaluate the entire warp in lockstep, we have to actually disable the even threads, execute the if branch on just the odd threads, then swap which threads are active and which threads are inactive, and execute the else branch on the other threads. So your code, which you thought was going to run 32 threads in parallel, actually is a little more sequential than you expected, because we have to run the if branch and the else branch in sequence on different sets of threads. So if that wasn't bad enough, there are some performance pitfalls also that have to do with the memory model. So I talked about global memory. So accesses from a warp to global memory take all of the addresses that threads within a warp are trying to access and try and combine those accesses, reads or writes, into as few transactions as possible. Where a transaction or a sector in the CUDA terminology is generally larger than a single read. So you have like, I think 128 bytes might be typical. So ideally, the threads within a warp will all request words that are fairly close together, and you can group these into as few sectors as possible. So if all of the addresses fit within one sector, then you just do one read from global memory, broadcast the results to all the threads, and great, it's pretty low latency. If the accesses fall farther apart, then we start having to access more and more sectors. Yeah.
Your use of the pronoun you confuses me. You the programmer, you the compiler, you the hardware, you what?
I wasn't aware of my usage of you, so I'm trying to now reconstruct exactly what it is.
You have to group.
Okay, yes, the hardware in this case. So the hardware is attempting
These pronouns are it.
Yeah. Yes, so the you, meaning the programmer, specify the memory access pattern. The hardware then tries to group this into as few sectors as possible. Yeah, thanks. So if the addresses are farther apart, then we have to perform more reads, more sectors, and the latency grows. So in the worst case, the 32 threads within a warp would access very distant addresses in memory, and we'd have to perform 32 separate reads. So this isn't that counterintuitive a performance property. It's just locality is good. Okay, we knew locality is good. Hopefully, if you're a relatively experienced sequential C programmer, you know locality is good. Shared memory is a little bit more counterintuitive. So shared memory is divided into 32 banks and hardware, where the banks can all be accessed concurrently, but multiple accesses to different addresses within the same bank have to be sequentialized. So if we perform 32 consecutive reads, 32 consecutive words, that happens to map to 32 consecutive banks, and we can perform all of those reads in parallel. On the other hand, if you have the worst case, you request 32 separate addresses, all that map to the same bank, and we have to access that same bank 32 times sequentially. And none of this is necessarily obvious to a sequential C programmer who's just getting into CUDA. It's all, if you read the CUDA documentation, it's there, but it's all not specified very clearly or very formally. NVIDIA is notorious for keeping the exact semantics of everything that's going on under lock and key. So it would be great to have a more formal model for being able to reason about the performance of CUDA kernels, and especially to be able to predict it statically. So that's a lot of what I'm going to talk about today. So first we have cost semantics that essentially tells you what's going to happen. You run your kernel, and it helps you reason about the performance of it. That's more of a simulation. It's a dynamic cost semantics. We would like, ideally, to be able to reason about our code without either running it or simulating it on a formal semantics. And so that's when I get to the second part of the talk. I'll talk about this static resource analysis. So static predictions of the performance of your code that attempts to approximate the model in our cost semantics. And so there's a formal correspondence between these two. This is implemented in an analysis tool that we call CUDA for resource-aware CUDA. And all of this part of the talk is based on my POPL 2021 paper with Jan Hoffman. So being that this is part of the talk is based on a POPL paper, I'll give the warning that there will be PL. I will try to keep it to a minimum and try to step through it as much as possible, but I do want to be formal, so it's not possible to avoid it entirely. So I know that the PL notation can be off-putting to people who are not PL people, so fair warning there. Then I'll talk about, briefly at the end, more recent work that some collaborators and I are working on applying this not to efficiency properties for maybe poorly written kernels, but actually to higher stakes things where we can actually leak information through these performance properties. And we want to reason about information security, so making sure that those leaks through the performance of your code don't happen. So let me talk a bit about the cost semantics. So cost semantics for a language in general defines how the program operates. So a formal description of the operation of a program extended with cost behavior. So not only what value does your program return, but also how long, or in general in units of cost, abstract kind of resource units, how much does it cost to execute this program. So in PL terms, we generally specify this with a big step operational semantics, just kind of a statement of this form. So I'll use the notation on the left to mean starting with heap sigma, if we evaluate the expression E on the set of active threads T. So this could be an entire warp, or it could be a subset of the warp if we've diverged and deactivated some of the threads. And resource metric M, I'll talk about the resource metric more in a minute. We get the result R, and all of this execution takes cost C. So our heap sigma is mapping from heap locations to values. The resource metric M is an assignment of non-negative rational costs to each operation that your program might perform. So this is our way of specifying what exactly do you mean by cost. Are you just talking about memory access cost? Are you talking about number of certain kinds of operations? So we can abstract over this parameter that specifies exactly what costs we're talking about. The result is a value for each thread. Every thread may return a different value. And the cost is a non-negative rational number. So this is the semantics for expressions, which don't update memory, but do return a value. We also have statements, which don't return a value, but do update memory. So in the semantics for statements, we don't get a result, we just get a new heap. But otherwise, the semantics are similar. So here's where I get into the PL, because I do want to briefly talk through a couple of the inference rules that we use to define this judgment. If you're not accustomed to reading inference rules, you can read them from top to bottom. So if all of the premises above the line are true, then we can conclude the statement below the line. So I've shown two of the rules for modeling if statements. So the first one, if we evaluate the condition and the result is true for every thread, then we just evaluate the else, the then branch using our semantics for statements. Return the new heap that we get from running the then branch, and we add together the cost that we got from running the expression, the cost that we got from running the then branch, and then also this constant cost that whatever the resource metric says is the constant cost for executing an if statement. If we don't care about the cost of executing an if statement, that might be 0, but in general, we might charge some constant amount for that. There's a totally symmetric rule for if all the threads evaluate to false, and we just evaluate the then branch. But if we have a warp divergence where some of the threads evaluate to true, so we'll call this T sub T, and some of the threads, the condition evaluates to false, so we'll call this T sub F. So we evaluate the then branch on the threads T sub T. Then after this, sequentially, so we model that this is sequential by threading the resulting heap into the execution of the else branch with the set of threads T sub F. And that becomes our new heap. And then we add all the costs together. So we get the cost of computing the condition, plus the constant cost of doing the if statement, plus the cost of executing the then branch, plus the cost of executing the else branch, plus there's some constant cost for encountering a divergent warp. Doing that masking and unmasking of threads isn't free, either in actual hardware or in our model. Well, I guess you could set this to 0 and choose it to be free, but you also have the option of charging for it. I'm not going to go through this rule in detail, but just one more thing I wanted to say about resource metrics is that most of the resource metrics are just a constant, so mif, mdiv, but some of the resource metrics actually take an additional parameter. So in the case of the operations reading and writing from global memory, that parameter is the number of sectors that are accessed. So the cost memory latency will depend on the number of sectors. And for reads and writes to shared memory, the cost or latency will depend on the number of bank conflicts. So we have that as an additional parameter to that that element of the resource metric. Okay, that's all I have time to say about the cost semantics. So I'll talk in a little bit more detail about the static resource analysis. So the technique we use is called automated amortized resource analysis. And the way we use this, at least, you can think of it as a way of automating the potential or physicist method of amortized analysis, which I'm sure all or most of you have seen in at least like an undergrad algorithms class, but just as a quick refresher, the technique is assign a potential Q, which you can think of as a potential energy in this analogy, to every state of the program. And programs should tend toward lower potentials. So we run down this hill, and the difference in potential between the starting state and the ending state is what we've used to pay for all the operations that got us there. So that difference between the starting potential and the ending potential is a bound on the cost of executing the program. The way we turn this into a static analysis is using what we call quantitative Hoare logic. So a standard Hoare logic is a logic for reasoning about statements about programs. So in general, we use this kind of triple where the thing in curly braces before the statement S says what's true before we execute S. This thing in curly braces after S is what's true after S. So in a standard Hoare logic, these things before and after are just logical statements about the state of the program, the state of the heap, state of local variables. These might be things like before we execute S, x is greater than 0. After we execute S, x is equal to 0. Maybe S was something like decrement x until it's 0. In a quantitative Hoare logic, we also add a potential function before and after execution. And the soundness theorem for this is that if we actually then take our, so this is something that we reason about statically, but then if we actually evaluate the program using our cost semantics and get a cost C, that cost should be less than the difference between the starting and ending potential that's predicted by this quantitative Hoare logic. So that's mostly taken from this 2015 paper. What breaks when we try to port this over to CUDA? Well, I said that these Q functions are functions of the state of the program. Well, the state of the program is now much, much larger because every thread of your thousands of threads has a separate copy of the state. So treating this as just a straightforward function of the state of your program is probably not a scalable solution. So what we do instead is make an observation about CUDA programs. So in most kernels, the variables that we actually care about tracking potential for, so for example, loop counters, parameters that are going to be used as loop bounds, things like that, these are really the things that determine how much this execution is going to cost. Other variables that just carry data around are usually not so important for this potential analysis. The observation is that these sort of important for the potential analysis variables, like loop counters and bounds, tend to be uniform across threads. So those tend to have not different values for each thread. And so we'll just track the potential for the variables that are uniform across all threads. So we add a third component to these pre and post conditions, which is x, the set of variables that we can statically know to be uniform across all threads, both before and after executing x. And we'll restrict the domain of the potential function q to operate only on x. So now, assuming that that x is actually the set of uniform variables, or is at least an approximation of the set of uniform variables, then we have the same soundness theorem from before, that our now restricted q is an appropriate upper bound on the actual execution cost of the program. And we've proven this theorem both on paper and in the ROC proof assistant. Not only that, we've also implemented it in a tool called CUDA, which we built in OCaml as an extension of the absinthe tool, which did this quantitative Hoare logic for C. So the general structure of the tool, it takes a CUDA kernel and a resource metric, performs some abstract interpretation to figure out the P part of that quantitative Hoare logic, the logical conditions. So in particular for CUDA, this means things like doing reasoning about the indices that we're going to use for memory accesses to figure out how many bank conflicts there are going to be. And then we lower it in a form that can just get passed into Absinthe. So once we have that information, Absinthe propagates the information about potential functions. So I didn't show any rules for any inference rules for that quantitative Hoare logic, but the rules basically place constraints on how potential should flow through a program. So it generates that set of constraints and then converts it to a linear program, which we can pass to an off-the-shelf linear program solver, and it spits out a bound. So now that we've implemented that, I can present some empirical results. So we tested this on 14 benchmarks, some from the CUDA sample kernels that come with the CUDA SDK. Some were written by us for this purpose, and some we found from the literature. So we used 4 resource metrics. One just counts the number of sectors or global memory transactions. One counts the number of shared memory bank conflicts. One counts the number of times you encounter these divergent warps, where different threads within a warp will take different paths. And then we have a metric we call steps, which attempts to combine the other 3 into kind of an approximation of running time. To get a sense of exactly what we're trying to evaluate here, it's important to remember that there's the actual ground truth. How many bank conflicts are there if you actually run the kernel on a GPU? This is something we can profile with tools provided by NVIDIA for at least these first 2 metrics. The second 2 metrics, there isn't really as direct a way to profile those. But we do profiling for these first 2. Then we have 2 approximations of that ground truth. So we have the simulation that we get from our cost semantics, which we tried to make it as faithful a model as possible to what's actually going on, but that needs to be validated empirically. And then we have the prediction from CUDA, which is based on this quantitative Hoare logic. So we proved that that's a sound upper bound of the simulated cost. We didn't prove anything about how tight a bound, so we'd like to empirically evaluate how tight a bound that is. And we also don't have any relation between the prediction and the actual ground truth. So if, for example, our simulation is way off, it's possible that the prediction is not even a sound upper bound of the actual cost, although we'd hope that the simulation is close enough that this actually is a sound upper bound. So we first evaluate this. How close is the model to reality? And the answer is pretty close. So this is the absolute error between the simulation and what we actually profiled, averaged over a few input sizes to each of these benchmarks. And with 1 or 2 exceptions, the error is within about 20–30%. I will also note that in almost all cases, it was an overestimate, which is what we hoped. We want a sound upper bound, so we would hope that if it's going to be off in one direction, our cost model is off high, and it almost always was, except in a couple of odd cases where it was under by a very small amount. And next on, so this is for the global memory sectors. Our prediction minus the actual profiled result. So this is going in this stack all the way from here to here. So what's the difference between prediction and actual? And also with the analysis time. Analysis times are generally under a second, except for some of the more complicated kernels. And errors are still pretty good. In fact, in a few of these cases, if we kind of compare these tables, the error between the prediction and reality is the same as the error between the simulation and reality, which means that all of that error is actually coming from our cost model and not from the prediction, which is actually a prediction of the cost from our cost model. So the prediction is perfect. It's just that the model is a little bit far from what we're actually trying to model. So here's what that looks like for the matrix multiplication benchmark over several different input sizes. So you can see it remains within basically a constant factor of the actual worst case. For bank conflicts, the story is a little bit more inconsistent. So on kernels with no bank conflicts, our tool is very good at predicting that it has no bank conflicts. If there are bank conflicts, we sometimes get a pretty drastic overestimate of the number of them. One good story is this histogram benchmark, which has an interesting, fairly complex worst case performance in terms of number of bank conflicts, and we do predict it accurately. So in the interest of time, I'm not going to talk too much about that. But one interesting thing is that there's a difference between the worst case and random instances, which shows the importance of static worst case predictions rather than random testing. But I want to get to raise the stakes a little bit and talk about the ongoing work with my colleague, former colleague now, Farzana Darakhshan at Illinois Tech, where I was until a couple months ago, and our co-advised student, Goda. And so we're working on seeing, OK, well, can you use this small performance differences based on these performance bottlenecks we talked about to leak information? So as an example, let's use AES encryption. So one part of the AES algorithm is performing transformations on a round key. The round key is private. And this is often implemented by looking up bytes of the round key in a table to perform some transformation on them. And then you do additional operations on the transformed bytes. So in a GPU implementation, it makes sense to store the lookup table in shared memory. But now we have the problem where the number of bank conflicts, and therefore the latency, depends on the actual bytes in our round key. And so by looking at the latency, you can get information about what the key was. And so this isn't a purely theoretical thing. People have actually experimentally performed this attack by they were able to reconstruct the round key by just taking end-to-end encryption time. So we'd like to guarantee a property called non-interference, which is that if you take two runs of a program whose start states differ only on secret information, then the public outputs shouldn't differ. Where here we're taking public output to mean not just the actual answer, but also observable timing things like bank conflicts. So our solution is in two parts. So we have a relational version of our quantitative Hoare logic, which bounds not the actual execution time, but the difference between two execution times. So between two different pieces of code, or between two runs of a piece of code, possibly two runs that differ on secret inputs. So you can see that this would be useful. So we could just stop there and say that non-interference means your relational Hoare logic returns 0 for any two versions of the code that differ only on secret inputs. That's a perfectly good definition of non-interference. It's a little unwieldy to work with because these Hoare logics generally are kind of complex analyses. They require a lot of heuristics, a lot of programmer annotations. We'd much prefer to work with something like a security type system, which tracks the security level of variables and expressions through a program and disallows insecure operations on them. So in this case, an insecure operation might be something like if you use a secret in a conditional, you want to make sure that the two branches of the conditional are guaranteed to take the same amount of time. Otherwise, there's a possible timing leak. And at that point, then we'll call back into this relational Hoare logic to verify that condition. But we use just much more fine-grained, controlled instances of this of the more powerful logic. All right, and that's, I think, almost the end of my time. So I'll stop there.
If I have NCU to tell me the shared memory, bank conflicts, whatever numbers, how does our CUDA help further?
Right. So CUDA will tell you the worst case number of bank conflicts or whatever your metric is without running the program. So it's not a profiling tool. It's a static tool that will actually give you a guaranteed, well, modulo the difference between the simulation and reality, but otherwise a guaranteed worst case upper bound. Yep.
Have you been able to use this this performance analysis system in order to perform auto tuning?
Yes. So this is work I thought about adding a slide on this, but I decided not to. So I'm glad somebody asked about it. So this was work that a former undergrad of mine presented at a workshop co-located with PPOP 2024, where we performed some kind of off-the-shelf optimizations, more or less at random, on a kernel, and get a bunch of candidates that may be better, may be worse, may be the same. And then we just run CUDA on all of them and figure out which of those is likely to be the best under some conditions. So it's still kind of a proof of concept, but we were able to do a little bit of that.
Okay, any more questions? Thank you again.